Hello, hello, welcome back. Today we will be solving Physics SL Paper 2 for November 2016, time zone 0. So it's going to be 1 hour and 15 minutes long, and calculators are allowed. So let's get started. Question number 1. Okay. A tennis ball is hit with a racket from a point 1.5 meter above the floor. Ceiling is 8 meter above the floor. Initial velocity of the ball is 15 meter per second at 15 degree above the horizontal surface. Assume that air resistance is negligible. So here the situation is, everything is clear. So there's 80 meter distance between the ceiling and the floor, and the height of the person is around 1.5 meter, and the angle of inclination is 50 degree, and he throws a ball at a resultant velocity of 15 meter per second. Determine whether the ball hits the ceiling. Okay. Now the ball will hit the ceiling if the distance between from here to here. So let's find out what is the distance that the ball needs to travel in order to hit the wall, the vertical distance that the ball needs to travel before hitting the wall. So it will be the total distance, which is 8, minus the height of the person, which is 1.5. So this is going to give us 6.5 meter. Okay. Now, first of all, we are only concerned with the vertical components of the velocities and the distances. So we have the limit for the vertical distance. We just need to find what is the maximum vertical distance that the ball can travel. Yeah. So let's find it out. So first of all, we need to resolve this velocity into two components. So you can always draw this right angle triangle. Here we have an angle, so let me draw a bigger diagram here. So this is the resultant velocity. So you can always draw this right angle triangle with horizontal and vertical component of the velocity. So one of the component will be horizontal, the other one will be vertical, and they must be perpendicular to each other. So the angle of inclination is 50 degrees Celsius, and here we have the velocity, which is 15 meter per second. Okay, so again use SOHCAHTOA, hypotenuse opposite. So this one will be 15 sine of 50 degree, whereas this one will be hypotenuse opposite adjacent. So adjacent over hypotenuse is cosine. So this one will be 15 cos of 50 degree. I suggest you pause the video here and then think about how we got this opposite over hypotenuse and adjacent over hypotenuse. So just for the reminder from your SL mathematics, so this is SOHCAHTOA rule. So when you have a right angle triangle, the sine theta is a ratio of opposite over hypotenuse, and cos theta is a ratio between adjacent and hypotenuse. So this has to do with right angle triangle. This length opposite to the 90 degree is the hypotenuse. So if we have an angle here, the length opposite to the angle is opposite, and the rest here of this length is adjacent. Yeah, that's a concept. Okay, so now we have the vertical component of the velocity, this one. So this is the initial velocity, u. So our u is 15 sine 50 meter per second. So because we know the moment when the ball is released is going to decelerate because of the influence of gravity. So there's a gravity that is pulling the ball downward, because of which the ball is going to decelerate until it reaches some maximum height. At the maximum height, its final velocity is 0. So we have to use this concept that the initial velocity, the ball starts with some initial velocity, and at the maximum height, the final velocity must be 0 for the ball to stop and then return back to the ground. So the point where the maximum height is reached is the point where the final velocity is 0. That is the point of interest, because that will give us the maximum distance, vertical distance that the ball will travel, and then we will compare that maximum vertical distance that the ball can travel with the limiting distance that we have. So we're only limited to reach 6.5 meter, but if the ball goes beyond that, then it will definitely hit the ceiling. Okay. So now we will use a Suvag equation. So if you remember the Suvag equation, V equals to U plus V squared equals to U squared plus 2AS. So show you where to get this equation from. So if you go back to 2.1, so we are using this equation. Why are we using this equation? Because there is no time component in it. So we are avoiding any information about time. So since time is not given to us, so we will avoid this, and this one. So V squared equals to U squared plus 2AS. A is the acceleration and S is the displacement. Okay, now what we need to find is the vertical displacement that the ball will travel at till it reaches the maximum height. So try to make S the subject. So if you rearrange the equation, S will be equals to V squared. U squared goes to the other side, becomes minus U squared, and then divided by 2A. Now just sub in the values. So final velocity. So let me write it here. At height maximum. So at the maximum height, your V is equals to 0. Yeah. So at the maximum height, the final velocity is equal to 0. So this thing just becomes 0. So we have 0 minus initial velocity is 15 sine 50. So it's 15 sine 15 degree whole square divided by 2A. Now A is the gravitational field strength, which is 9.81 and also negative. Why negative? Because this is opposing the direction of the motion. So the motion is upward, but the gravity is opposing the direction of the motion, so it's downwards. That's why we have to put a negative sign here. So, and now we just need to hit the calculator. So if we hit the calculator, it will be alright, so it's going to be 15 times sine of 50. So we have a result, and then we take the square, and then bracket close, divided by. So you can see there's a negative sign here, so this negative actually cancels out with this negative, so negative cancels out each other, it becomes positive. And on the denominator we have 2 times 9.81. So it looks like our sine of 50 is giving answer in radian, but our angle is in degrees, so we have to be careful with that. Let's see, sine of 90 is, yeah, it's still in radian, so we need to convert it into degree. So let's just check, sine of 90 is 1. Yeah, now it's correct. So 15 times sine of 50, and then bracket close, whole square divided by brackets 2 times 9.81, bracket close. So enter 6.73. So correct the 3 that's significant figure. The result is 6.73. Okay. So 6.73 meters. So that is the maximum height that the ball can reach. And as you can see, this maximum achievable height is bigger bigger than 6.5 meter, it means it will definitely go beyond the ceiling and it will hit the ceiling. So it will definitely hit the ceiling. Okay. Part B. The tennis ball was stationary before being hit. It has a mass of this much kg and was in contact with the racket for 23 milliseconds. Calculate the mean force exerted by the racket on the ball. So if you go back to the data booklet, so in order to find the mean force, we just need to use this equation. The resultant mean force acting on the ball is equals to rate of change of momentum. So it's change in momentum over change in time. So this time is actually the contact time, the time during which there is a contact between the ball and the source of the force. Contact time. So let's use that equation here. So we have our resultant force is equal to change in momentum over change in time, duration of the time. So as you remember, momentum is mass times velocity. Yeah, so momentum is mass times velocity. So change in momentum is due to change in velocity. So, but the change in velocity can also be further substituted as final velocity minus initial velocity. Now for our case, as you can see from the previous result, it says that the final velocity, the moment right after the ball gains impulse and momentum, it achieves a velocity of 15. So yeah, it achieves a velocity of 15, but initially it was stationary. The tennis ball was stationary before being hit. Right after it was being hit, it achieves a velocity of 15 meters per second. So the situation here is something like there's a ball here, and then initially the initial velocity is 0, so you can see it's stationary. Then when you hit it, it gains a velocity of final velocity of 15 meters per second. So that is the situation here. So this initial velocity is 0, and this final velocity is 15. So we can just replace it by mv. So change in momentum is due to mass times final velocity over duration of the time. Let's just plug in the numbers. So mass is 5.8 times 10 to the power negative 2. Our final velocity that the ball achieves right after it is being hit is 15 meters per second. Just make sure that everything is in SI unit. And the duration of the impact duration is 23 milliseconds. Make sure you convert millisecond into standard SI unit, which is second, by multiplying by 10 to the power negative 3. Now we just need to sub this thing in our calculator. So let's go back to our calculator. I'm just using this Chrome calculator now, but you can use your scientific calculator. Okay. 5.8 times 10 to the power negative 2, bracket close, multiply by bracket open, 15, bracket close, and the result is being divided by bracket open. So just make sure that you take care of these brackets, because brackets are very important here, at 10 to the power negative 3. Everything seems correct, so it's equal to 37.83, so it's around 37.826, so we have to approximate to round up or round up, approximate to 3 significant figures, so it's 37.8, and we are dealing with force, so the force unit is Newton. Yeah, so make sure that you also write down these units. Okay, explain how Newton's third law applies when the racket hits the tennis ball. So there's a ball here, and there's a racket here. So a racket and a ball. Newton's third law. So Newton's third law dictates that for every action there is an equal and opposite reaction. So you can just explain that, oh, if the racket exerts a force on a ball, then the ball will also exert equal but opposite force on the racket. So just make sure that you include these two important points, that the magnitude of the two forces that the racket and the ball exert on each other are the same and they are in the opposite direction. We can also consider the mark scheme. For more any details, you can see the force of ball on the racket is equal, so they have to be equal on each other and they have to be in the opposite direction. So that is what your 2 marks are for. They have to be equal in magnitude and opposite in direction, and they act on each other. So Newton's third law is always applicable, so it is applied in all type of situations. Okay, question number 2. Curling is a game played on a horizontal ice surface. A player pushes a large, smooth stone across the ice for several seconds and then releases it. The stone moves until friction begins bring it to rest. The graph shows a variation of speed of the stone with time. Okay, it looks like the friction is acting during this part of the motion, because initially the body was accelerating and then it reaches some point where friction starts to take place and then it starts to decelerate until the velocity gets to 0. The total distance traveled by the stone is 17.5 seconds is this much meter. Determine the maximum speed v of the stone. Alright, first of all, always remember, so if we have a graph of displacement versus time, velocity versus time, and acceleration versus time, in order to go forward, what I mean is, if you have a displacement versus time graph, and you want to achieve velocity, then you need to find the slope of the graph. So to move forward, you need to find the slope of the graph, or gradient, or differentiation, and in order to go in the reverse direction, you need to find the area in the graph. So imagine if you have a graph of acceleration versus time, and you need to find velocity, just find the area in the graph. So in our situation, we have a speed time graph, so we are here. What do we want? We want something, we have to do something with total distance. So we need to find displacement. So we need to go from here and take this path to get displacement. But to do that, we have to find the area in the graph. So this total area. So it looks like it's a triangle, and the area of a triangle is half base times height. So this is the total base of the triangle. It doesn't have to be right angle triangle. This is the total base, and this is the total height. Okay, so the total base is 17.5. Is it in SI unit? Yeah, it's in a second. And the total height is just V, so V is unknown. Whereas this total area under the graph is equals to distance. As you can see from here, in order to go from velocity time graph to displacement graph, you just need to find the area. So the area is a representation of total distance, and the total distance is 29.8 meters. Okay, let's rewrite this equation again. So we can replace this area. So call this area as capital A. Area equals to half, and we have the base, maybe call it just B, and we have the height, and height can be replaced by just V, right? Let's make V the subject. So in order to make V the subject, you can move this 2 up there, so 2A over V. So I like to do in this way, in the sense that first make the variable the subject that you want, and then in the end plug in all the numbers and then use your calculator only one time. So it just helps to eliminate and minimize any random or rounding errors. Now let's just plug in the values. So we have 2A and B. So B is the base, base is 17.5, and the area is 29.8. That will give us the maximum velocity that is achieved. So so we have 2 times 9.8 divided by 17.5, and the result is 3.41. 3 significant figures, 3.41. so the maximum velocity achieved is 3.41 meter per second. Okay, so we have our point of maximum velocity. Okay, 3.4. Part B. The stone has a mass of 20 kg. Determine the friction force on the stone during the last 14 seconds. So as I already explained, it is during the last 14 seconds. So is it 14 seconds? Yeah. If you subtract the 2 times, you'll get 14 seconds. So during the last 14 seconds, there's a frictional force acting on the body, because of which the velocity is decreasing. So the body is like decelerating until the velocity decreases to 0. And we need to find the friction force that causes this deceleration. So determine the frictional force. So whenever it comes to force, we always use the Newton's second law equation, which is that net force is equals to ma. So this is the equation that we will be using. So this force is actually the net force. In our case, it is the net frictional force that will cause the deceleration. We have the mass, we just need to find the acceleration, or in other words, deceleration, because the velocity is decreasing. We have the mass, we don't know what is deceleration. So if you look back at the graph and observe, this is a graph of velocity time graph, and this time we want acceleration, so we have to go forward and by taking this path, or in other words, finding the slope. So this time we are finding the slope of this graph so that we can get the velocity, the acceleration. So we have to find the slope from here to here for this line. Yeah. So we have to find the slope for this line. Not this one, because we're only considering the last 14 seconds during which the body is decelerating. So how do you find the slope? And in order to find the slope, you draw this triangle, and then you do rise over there. Okay, so let's just copy the triangle here. Okay, so let's draw the triangle here. So remember, there's a 3.5 here, there's a 17.5 here, so that last 14 seconds. And remember the final velocity that we calculated is around, this final velocity is 3.41, starting from 0. So 0 to 3.41. So we have a 0 here and 3.41, or in other words, the rise of the gradient is 3.41. So let's find the slope. So the slope is given by rise over run. So the rise achieved is 3.41, equivalent to final maximum velocity, and the run is 14 seconds. Okay, so that is our slope, and as you can see, this slope is equals to acceleration, as I already explained. So we can substitute this acceleration. Actually, it is deceleration, so we have to put a negative sign here. Now, why is it deceleration? Because it's a negative slope. It's a negative slope and the velocity is decreasing. So let's substitute everything into here. So mass is 20 kg, and the deceleration is multiplied by minus 3.41 divided by 14. Okay, let's just hit the calculator. So we have to do 20 times 3.41 negative 3.41 divided by 14. So 20 multiplied by 3.41 divided by 14. Enter 4.87 with a negative sign. Yeah. So the result is negative 4.87. It's a force, so it has to be in newtons. 4.87 Newton is the resistive force that is required in order to decelerate the body from 3.41 meter per second to 0 in the last 14 seconds. Generally, the energy dissipated due to friction during the last 14 seconds. Well, so what is going on here is we know that there was a ball here and it starts from 3.5 and then it gets to rest. So final velocity becomes 0 here, and the initial velocity is 3.41 meter per second, and it achieves 0 velocity. It decelerates to 0 at 17.5 seconds, and it takes around 14 seconds to decelerate. So this is a situation here. In order for the body to decelerate, there must be some frictional force acting in the opposite direction. So call it F. We already have the friction force. So this one is the frictional force. So it is opposing the motion, and the motion is in the forward direction. So this is a scenario here. So this is a rough surface. This one. Okay. So the best way to solve this equation is there are actually two ways of solving this equation. You can either determine what is the work done. So work done is force times displacement in the same direction. So the work done against the frictional force. So we have the frictional force, which is 4.87, and multiplying by the distance traveled, this displacement. So frictional force times the displacement will also give you the energy dissipated in the last 14 seconds. But the problem with using this equation is we don't know how much distance does it travel in the last 40 seconds. Well, you can do that by calculating the area under this graph. So this section of the area. For the last 14 seconds, just find what is the area of this triangle. Not the entire triangle, but only this part of the triangle, because this is the distance that it travels during the last 14 seconds. And then just sub in into here. Or you can use simple energy conservation. So if you use simple energy conservation, you will realize that at 3.5 seconds, the start of the motion, the body has some kinetic energy because it has some velocity. And that entire kinetic energy is lost or dissipated to do work done against friction as the body decelerates to a 0 velocity. So you can say that the entire energy dissipated is because of the initial kinetic energy that the body had at the beginning of the motion. So that entire kinetic energy, which is equals to half mv squared, actually gets dissipated into work done against frictional force. So we can also use that. So that's what we have. So the mass of the ball is 20, and its initial velocity, because of which it had some kinetic energy, is this much. So the entire initial kinetic energy that the ball had before is dissipated and converted into work done against friction, and it gets dissipated as heat or other form of energy when the velocity becomes 0 here. So let's just see the calculator. So you have half, which is 0.5 multiplied by 20 multiplied by 3.41, and then take the square. 116.281. So it's 116.281 joules. Just round it up to 3 significant figures, so it will be like 116 joules. So 116 joules of energy is dissipated. So I repeat, you can solve this question in terms of two ways. You can either find the work done against frictional force, which is frictional force times the displacement, and that work done against frictional force is ultimately dissipated into other form of energy. But in order to use this method, you need to find what is the displacement or the distance moved during the last 14 seconds. And then you can achieve that by finding the area under the graph during the last 14 seconds. Or if you don't want to use this method, you can just simply find how much is the initial kinetic energy that the ball is is possessing at the start of the motion, because that entire kinetic energy is converted into work done against friction and ultimately lost as heat or other form of energy and dissipated as the body decelerates to zero. So we just need to find the initial kinetic energy, and that entire kinetic energy is dissipated as heat and other form of energy. Question number 3. Define internal energy. So internal energy of any substance, so you can have like any substance, can be solid, liquid or gas, is defined as the sum of the kinetic and potential energies of the particles. So the particles can be either atoms, molecules or ions, doesn't matter, but it is not the kinetic and potential energy of a bulk body, not the bulk body, but of the individual particles. So you used to say, define internal energy, it is the sum of the kinetic and potential energies of the particles. So if you also look at the data booklet, so the mentioning of the particles at atomic particle molecular level is very important. So mentions of atom molecules, yes, and then it is the sum of the kinetic and potential energies of the particles of the substance. Yeah. So let me explain more here. So kinetic plus potential energy. Now the kinetic energy of the particles is directly proportional to temperature, so it depends on the temperature in Kelvin. Whereas the potential energy depends on the average distance between the particles. Yeah. The bigger the distance between the particles, the higher the potential energy, and the bigger the temperature, and the higher the kinetic energies of the particles. Yeah. Because potential energy actually is due to the intermolecular forces of interactions between the particles that exist. So there is always some intermolecular forces of attraction and interactions between the molecules, and they're always like attracting each other. So if you want to increase the space between the atoms, then you have to overcome this intermolecular forces, and to do that you need to provide potential energy. Whereas the kinetic energy is half mv squared, so it depends on velocities, and velocity depends on temperature. So higher the temperature means the particles gets more excited. When it gets more excited, they travel faster, and faster they travel leads to higher kinetic energies. 0.46 part B, 0.46 mole of an ideal monatomic gas. So monatomic means single atom gas. So if you take chemistry, remember that all noble gases are monatomic gases. For example, you can have fluorine and xenon, those type of on the periodic table, I think is in the column 8. So all noble gases in the column 8, they are monatomic, so they don't form molecules. For example, in contrast to oxygen, oxygen doesn't exist as monatomic, it always exists as diatomic, O2. Or you can have ozone. So these are, ozone is O3. Chlorine, it exists in nature as a covalent bond between chlorine and chlorine. So this is molecule, 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 but the single chlorine is monatomic. So monatomic gas is trapped in a cylinder, and the gas has a volume of 21 meter cube and a pressure of 1.4 Pascal. State how the internal energy of an ideal gas differs from that of a real gas. So the main difference between an ideal gas and a real gas is that in ideal gas it is assumed that there are no intermolecular forces of interaction between the particles. So there's no intermolecular forces of interaction between the particles. But this is not true, impossible. There is always some form of intermolecular interaction between the particles. So the particles, either in gases, liquid, or solid state, they always try to attract each other. So that is what happens for a real gas. In a real gas, the gas particles always have some interactive forces between them, because of which potential energy exists. So the potential energy exists in real gases because there is some intermolecular forces of interaction between the particles. Whereas in ideal gas, because we assume ideally that there is no intermolecular forces of interaction, hence there will be no potential energy. So potential energy is gone from ideal gas. So as we already know, the internal energy, so internal energy is the sum of kinetic plus potential energies of the particles. Well, for an ideal gas, potential energy doesn't exist. It is zero because we assume there is no intermolecular forces of interaction. Hence, the entire internal energy of an ideal gas is entirely due to the kinetic energy. Whereas for real gas, both of them exist. So obviously, for real gas, the internal energy is bigger than that of an ideal gas. So we will say the internal energy of an ideal gas is smaller than the internal energy of real gas, because in real gas we also have to take into account of the existence of potential energies because they are intermolecular forces of interaction between the particles. So all gases are real gas in nature. There is no such thing as ideal gas, so it is only an imaginary ideal gas. So why do we use ideal gas? So that we can simplify the mathematics and we can use this equation PV equals to nRT. So the main assumption for using this equation is that a gas is an ideal gas. Now we cannot use this equation on real gas. Yeah. Now, then you should ask, like, okay, then if ideal gases doesn't exist, then why do we still use PV equals to nRT? The reason is because even if you have a gas which is real, you can always change some parameters to make it behave as close as possible to a real gas. For example, you can increase its temperature. When you increase its temperature, it means that particles are moving very fast past each other, so they won't have enough time to interact with each other. So like particles are moving very fast past each other, so they won't be able to develop strong intermolecular forces. You can also keep a very low pressure and low density. So by keeping a low pressure and low density, you make sure that there are enough large spaces between the particles. They are further distance apart. So the further away the particles are, the strength of the intermolecular force of attraction will also get smaller. So the weaker the force means the gas will behave more like an ideal gas, like negligible intermolecular forces of attraction. Part B. Determine in Kelvin the temperature of the gas in this cylinder. So we will assume that the gas is ideal. It's already given to us. It's ideal gas. Since the gas is ideal, we can use the ideal gas equation, which is PV equals to nRT. And we need to find temperature in Kelvin, so make temperature the subject. PV is as it is on the top, nR goes down there. So let's try to sub in all the values. So P is the pressure. So let's see how much is the pressure. So the pressure is 1.4 Pascal. So that's already in SI unit. Volume is 21 meter cube, already in SI unit. Divided by number of moles, so 0.46 number of moles. Multiplied by R. R is a molar gas constant, so it's given in the data booklet. So let me show you where can you find the value of R. So R will be here. Gas constant is 8.31. Here. Okay, now let's use calculator to sub in all these numbers and let's see what is the result. Okay, let's bracket open 1.4 times 21, bracket close, divided by bracket open 0.46 times 0.46 times 8.31 equal 7.69. So the temperature in Pascal is around 7.69 Kelvin. It's pretty low temperature. And you can see the temperature is kept quite low here. Yeah. The kinetic theory of an ideal gas is one example of a scientific model. Identify one reason why scientists find such model useful. Well, it's because it is easier to do the mathematics. It clearly simplifies the calculation, and the manual calculation becomes even more simpler. So it helps to explain complicated phenomena into a simple phenomena. So it's easy to explain. So it's just for the convenience of the scientists. So anything that, let's say that it becomes easy to explain, to simulate. So model used to predict, so it becomes easy to predict. and hypothesize, explain, simulate, and simplify. Yeah, that is why we use the kinetic theory of model. Okay, so kinetic theory of model states that like all particles exist at a certain temperature. So when they have certain temperature, the particles must be vibrating or moving randomly. If it is solid, then the motion is not random, but if it's liquid or gas, the motion is random. But they always move because they always have some temperature, and because they have some velocities, the particles, they will also have some kinetic energy. So that's the kinetic model theory. Okay, next one. Two microwave transmitter X and Y are placed 12 centimeter apart and are connected to the same source. A single receiver is placed 54 centimeter away and moves along a line AB that is parallel to the line joining XY. Okay, so the microwave XY, 54, and the receiver. Maxima and minima of intensity are detected at several points along AB. So constructive and destructive, constructive, destructive. So all these interferences are observed and they always occur in alternating order. Explain the formation of the intensity minima. So minima happens when destructive interference between coherent waves occurs. So destructive interference happens when the two amplitude cancel out each other, and they cancel out each other if the two waves are 180 degrees at the phase difference. So the phase difference between the two waves have to be 180 degrees. Let me show you how. For example, if this is one wave and if another wave coincides such that it is 180 degree at the phase difference, so this amplitude and this amplitude, they just cancel out each other, giving us a wave that has zero amplitude. So that is minimum, no intensity. So the two intensities or the two amplitudes just cancel out each other. And this occurs when the two waves are 180 degree at a phase difference and they destructively cancel out each other, giving us zero intensity. So you can see minimum occurs when we have a destructive interference, and it occurs at the minima waves meet 180 degree phase difference. So they must be out of phase by 180 degree. The distance between the central maximum and the first minimum is 7.2 centimeters. So explain what is happening here. Take back the red pen. Okay, so this is the wave that is incoming. It has some wavelength lambda, and this is the slit width. Call it small d. And you have a screen here. This is the central line, an imaginary center line. So here you always have a maxima. There's always a maxima here because when the wave comes from here and here, the path difference between the two path lengths is always zero, because you can see it forms the isosceles triangle and these two lengths are the same. So if the two path lengths are the same, then the difference is zero. So when the path difference is zero, you always get central maxima, which is constructive interference. So right after constructive interference, you have destructive interference or minima. The amplitude just cancel out each other, and then after destructive interference, you again have maxima, which is constructive, and then you again have destructive. So they occur in alternating order. So destructive, I'm representing destructive by this dark spot, which means that intensity is zero, because the amplitude cancel out each other, and these bright spots are constructive interference, maxima. The distance between the central maxima, so always remember, this is not central maxima, because this is a maxima which occurs at the center point, but since it always stays there, so it has no special meaning. What central maxima means are these two, this one, and this one. This is central maxima. So in other words, this always happens at 0, so n0, so the first maxima, and this one is the central maxima, which occurs at n1. So the distance between the central maxima, this one, and the first minimum, so this is the first minimum, this one. You can either choose this one also, but let's just choose this one. It doesn't matter if you choose the bottom one or the top one. So the distance between the first maxima and the minimum this distance is something, right? It's 7.2, so this is 7.2. And also remember the half the width between central maxima, so this is central maxima. Distance between this N1 and this N1 is called 2s, but half the width of central maxima is just s. And the equation from the data booklet is s equals to lambda capital D over small d, whereas this distance is capital D. Yeah, let me show you where the equation is. Where does the equation come from? So if you scroll back at the data booklet, here, s equals to lambda d capital D over small d. Okay. So calculate the wavelength of the microwave. So we need to make wavelength the subject. So wavelength is going to be small d can go up there, and capital D goes down there. So lambda equals to s. So where is s? So s is the half the distance or half the width between central maxima. But we are given this distance between first central maxima and the first minimum, which is 7.2. But as you can observe, s is double than that. So we have to multiply by 2. So this s will be 7.2 multiplied by 2. We have to take twice this distance, because this distance is half of this distance. So s can be replaced by 7.2 times 2. And then we have the small d, which is the slit width. And how much is the slit width? So if we scroll back, yeah, xy. So 12 centimeter is the slit width. So we can put 12 centimeter. As you can see, everything is in consistent here in centimeter and centimeter. This is big D and this is small d. This is also centimeter. So no need to convert into meter, because centimeter just cancel out each other. And our final result will also be in centimeter. Okay. So you can keep everything in centimeter. Then the final wavelength will also be in centimeter. And how much was capital A? 54 centimeter. 54 centimeter. Okay, so let's just hit the calculator. So we have 7.2 times 2 times 12 divided by 54 under 3.2 centimeter. This will be 3.2 centimeter is the wavelength. This way, approaching toward the slit. Okay. Next one. Radio waves are emitted by a straight conducting rod antenna aerial. The plane of polarization of these waves is parallel to the transmitting antenna. An ideal antenna is used for reception. So just why the receiving antenna needs to be parallel to the transmitting antenna. Well, in order to absorb maximum intensity. Otherwise, if it's not parallel, then it will block the incoming transmission. So, for example, if this is the antenna, and imagine these are the waves. So this is the plane of the wave. So the plane is like flat. It's a flat plane. And this is the plane of the antenna. So the plane of the antenna will be parallel. So the two options can either be parallel or it can be perpendicular. So you draw both options. So another antenna, maybe it has perpendicular component. Okay, so if it's parallel, then all these waves will be able to pass through them. So maximum intensity can be received. But if it's perpendicular, then you can see it will be blocked. So that is the reason. So that's why the receiving antenna needs to be parallel in order to absorb maximum intensity of the incoming light or incoming radio wave, electromagnetic wave. Let's see what does the maximum says. Should be similar. The component of the polarized signal in the direction of the receiving antenna. Yeah. Why? Because it has to be the maximum. The intensity received is maximum only when the plane of polarization of the incoming light is parallel to the receiving antenna window. Yeah. Why they have to be parallel to each other? So that maximum intensity can be absorbed. Yeah, so the component of the polarized signal in the direction of the receiving antenna so that the maximum intensity is absorbed when both are parallel. Yeah. Okay, otherwise the perpendicular component will block the incoming plane of polarization. Next one, the receiving antenna becomes misaligned by 10 degrees to its original position. As you see now, the antenna window, so this is the incoming electromagnetic wave. Now instead of parallel, it is maybe at a 30 degree. 30 degrees. You can see some of it will be blocked and some of it will be allowed to pass through. So since the incoming light is already plane polarized, we can definitely use the polarization equation. The power of the received signal. So this is the final intensity. The intensity received at the other end is I, which is 12 microwatt. Calculate the power that was received at the original position. So the initial intensity, call it I naught. So let's use the plane polarization equation. Why we can use that equation is the reason is because the light is already polarized. So the incoming wave is already polarized. It is not unpolarized light that it has planes in all different directions. So when the electromagnetic wave is plane polarized, we can always use this polarization equation. This one. So let's copy this equation in our note. Let's copy it here. So we will use I final intensity equals to initial intensity cos square theta. Okay, so we have final intensity, we need to find initial intensity, so just make initial intensity the subject, so it will be final intensity divided by cos square theta. Just for your information, the intensity is equals to power over area. So it's the ratio of power over area. Power distributed across a certain area. And the unit will be watt per meter square. This is the unit for power. Oh, sorry. Alright, let's leave it. Okay, this is the unit. Okay, let's sub in the values. So keep the intensity as microwatt. If you keep final intensity as microwatt, then your initial intensity will also be in the same unit as microwatt. No problem. So initial intensity is 12 microwatt and our angle is cos of 30. Just be careful with this square. First you need to take cos of 30, then take the square. A lot of students make mistake that they take a cos squared of 30 and gives you a wrong result. So in other words, this is just like first take cos of 30 degree and then take the whole square. This is what this thing means. Okay. Let's use a calculator now. And also make sure your calculator is in degree mode because our angles are in degree, not radian. Okay, so we have 12 divided by bracket open cos of 30, bracket close again, square. Enter. 16. Okay, so this is 16 microwatt. So let me explain more like on a diagram. It looks like the initial intensity is 16 microwatt, and the final intensity after passing through the polarizer, which is not parallel but it is inclined at an angle of 30 degrees, is 8, wasn't it? 12. 12 microwatt. Okay? Yeah, plane polarization. So around 4 microwatt has been blocked by this polarizer, as it is oriented at 30 degrees. Calculate the minimum time between the wave leaving the transmitting antenna and its reception. Well, since it's an electromagnetic wave, it's a radio wave. It's a radio wave. All radio waves are electromagnetic waves. So, and all electromagnetic waves travels at a constant speed of equivalent to the speed of light, which is 3 times 10 to the power of 8 meter per second. So we know that all electromagnetic wave travels at the same speed of light. We have the speed of light, and it is also constant, so there's no need to use the like equation. Just use this equation: speed equals distance over time, because the speed is constant. And the distance between the transmitting antenna and receiving antenna is 56 kilometers. So we have the speed, we have the distance, we can just find the time. Minimum time. So speed equals to distance over time. Time equals to speed, distance over speed. The distance was 56 kilometer. So convert kilometer into meter by multiplying by 1000. And the speed is already in meter per second, which is speed of light, 3 times 10 to the power 8 meter per second. So I need to write the unit here. So let's just use a calculator again. 56 kilometer is 56,000 meter divided by 3 times 10 to the power of 8 speed of light. Well, that's pretty quick. This is actually very short time, 0.0001866. Let me write it again. So approximately the time is factor 3 significant figure will be 0.000187 seconds. Yeah, that is the approximate time that it will take for the electromagnetic radio wave to reach from the transmitter to the receiver. Yeah, use the speed of light as the speed for the wave, and it's constant. Define gravitational field strength. Well, gravitational field strength is given by this small g, and gravitational field strength is a ratio between the gravitational force that acts on per unit mass. So it is the ratio of the gravitational force acting on per unit mass. It has a SI unit of Newton per kg, or it is also equivalent to gravitational field acceleration, so which is meter per second square. SI unit, as you can see, force, the unit for force is Newton, and on the denominator we have mass, which is in kg. When kg goes up, it becomes -1. So Newton per kg, you can use either this, or you can use acceleration, because you know that g is also equal to 9.81 meter per second square. So the acceleration is also a unit for gravitational field strength. Gravitational field acceleration, gravitational field strength. You can use any one. Let's see, look at the formal definition for gravitational field strength. It is the gravitational force per unit mass. So the mass has to be small. So the mass has to be small enough to just sense the gravitational force but not disturb it. A planet orbits the Sun in a circular orbit with the orbital period t and orbital radius r. The mass of the Sun is m. Show that the time period t is equal to this much. Okay. Now what is happening is there is a Sun and there is a small planet. So let the mass of the Sun be capital M. Let the mass of the small planet be small m. And this planet is revolving around the Sun with some velocity. So it's called as the tangential velocity. You can see this velocity is tangent to this circular motion that is produced. And there is a radius between the radius of the orbit. So there's a radius of the orbit. And because two big masses are involved, there must be some gravitational force of attraction. So gravitational force is always an attractive force. So also realize, because there is a circular motion involved, for a body to move in a circular motion, there must be a centripetal force also acting toward the center of the circle. So there must be a centripetal force, which is the net resultant pure amount of force acting toward the center of the circle. Now the question is, who is responsible to provide this centripetal force? Is there any rope attached between the sun and the moon that can provide tension, which can be equivalent to centripetal force? No. Is there any rocket attached at this mass that can provide the centripetal force? No. So in this scenario, the centripetal force, which must be there, is actually provided by the gravitational force of attraction between the two masses. So we can say that we need centripetal force for the body to move in circular motion, and that centripetal force is provided by the gravitational force of attraction between the two bodies. And the formula for, as you know, that force is equals to ma, so we can replace Fc by mass times acceleration, but the acceleration here is unique, it is centripetal acceleration. And the gravitational field strength, the formula is Gmm over r squared. So this is given in the data bubble. Let me show you where it is. So Gmm over r squared is gravitational force of attraction, which is here, Gmm over r squared. And the centripetal acceleration is this one. So you can use either one of them, but we will use the one that has the time period in it. So we will use this one. Centripetal acceleration is 4 pi square r over t squared. So t is the time period. So we will replace this centripetal acceleration by 4 pi square over r square over t square. Is it correct? Oh no, there's no square here. So ignore this square. Equals to Gmm over r square. These two masses can be cancel out, and just rearrange the equation, so make t squared the subject. So t squared is equal to, so let's do cross multiplication. 4 pi squared, r squared times r is r cubed, divided by gm can go down there, comes this. Now in order to get rid of the square, you have to take square root on both sides. This and this cancel out, so ultimately this capital T is equals to square root of 4 pi square r cubed divided by gm. There we have it. So the time period is equal to square root of 4 pi square r cubed over gm. Okay? Yeah. So we have to use this circular motion and gravitational force concept together. Just make them equal and then make t the subject. The Earth orbits around the Sun. So this is the Earth-Sun orbital problem. In almost a circular, with the radius, so we have a circular motion happening here, and we have the radius of the orbit, so this is the radius of the orbit, and estimate the mass of the Sun. So as you can see, this capital M is the mass of the Sun. So this is the Sun, and let this be the Earth. Sun, Earth. So we already have this equation. Since we are interested to find the capital M, we need to make this capital M the subject first. So let's just copy this equation as it is. So t equals to square root of 4 pi square r cubed divided by capital Gm. Take square on both sides, we have t squared equals to 4 pi square r cubed over Gm. When you take square on both sides, the square root just cancels out. Take square root on both sides, then make this capital M the subject. So capital M equals to, capital M can take this position and t squared can take the capital M position, so it will be 4 pi square r cubed divided by gt squared. Now let's just sub in all the numbers. So we have 4 pi square r cubed, so r is the radius of the orbit, which is already given to us between the Earth and the Sun, which is 1.5 10 to the power 11, divided by g is the gravitational universal gravitational constant, which we can find from the data booklet. So we just scroll up all the way to the first page. So capital G is here. Gravitational constant 6.67 10 to the power negative 11. So it is 6.67 times 10 to the power negative 11. And then we have t squared. So here, think about what time period should we use? So this is the Earth and Sun problem. Earth orbit around the Sun. How long does it take for an Earth to complete the orbit around the Sun? Is it 365 days, 1 year, or is it 24 hours? 1 year. So the time period is actually 1 year. It takes 1 year for the Earth to complete the orbit around the Sun, and it takes 24 hours for the Earth to complete its own rotation about its own axis. So Earth rotates about its own axis in 24 hours time period, whereas the Earth orbit around the axis of the Earth or of the Sun, and then it takes 1 year. So just make sure that you realize you can distinguish between 24 hours and 1 year. It takes 1 year for the Earth to revolve around the Sun, and it takes 24 hours for the Earth to rotate about its own axis. So they're different things. So in this time we are orbiting around the Sun, so we will take 1 year as a time period. So 1 year has 365 days, and 1 day has 24 hours, and 24 hours, 1 hour has 60 minutes, and 60 minutes has 1 minute has 60 seconds. So we have to convert 1 year into second. So I repeat, 1 year has 365 days, each day has 24 hours, 1 hour has 60 minutes, and 1 minute has 60 seconds. So this will give us 1 year in seconds. And just input all of this in calculator. After you input everything in the calculator with the correct brackets, you should get an answer of 2 times 10 to the power of 30 kg. 2 times 10 to the power of 30 kg. That is the mass of the Sun. Just make sure that you put these brackets in the calculator. I also just use a fraction on the calculator if it has the option. Okay, so the orbital time period of the Earth around the Sun is 1 year, whereas the orbital time period of the Earth revolving around its own axis is 24 hours. 1 day. Question number 7. The graph shows how current I varies with potential difference V for a resistance R and a non-ohmic component T. You can see T is non-ohmic because it is not a straight line passing through the origin, whereas the resistor R is definitely ohmic because it follows the condition that it is a straight line passing through the origin, so current and voltage are directly proportional for R but not for T. State how the resistance of T varies with the current going through T. So the formula for the resistance is resistance equals to V over I. Okay. Now if you look at the graph for T, you can see that it is actually curved in the upward direction. So it's curved upward. When it's curved upward, it means the upward direction, which is the current. So the current increases at a much faster rate than the voltage. So the voltage is also increasing, right? So the voltage is increasing, the current is increasing as we move along this curve. But since the direction of the curve is concave upward, the current, which is in the upward direction, increases at a much faster rate than the voltage. So if the denominator increases at a much faster rate than the numerator, so what's going to happen? Eventually the resistance will drop. Okay. State how the resistance of T varies with the current. So as you increase the current through the component T, the resistance decreases because the current is in the denominator, and the current increases at a much faster rate than the voltage because it is curved upward. If it was curved downward, like something like this, then it will have been the other way around, that as the current increases, the resistance increases. But this time, as the current increases, the resistance decreases. As you can see here, RT, the resistance of T decreases with increasing current. Deduce without a numerical calculation whether R or T has greater resistance at I 0.4. So when the current is 0.4, so we are here. Okay, so let's zoom in a little bit. So this is the voltage for T, and this is the voltage for R. So this is the voltage for T, and this one is the voltage for R. Yeah, okay. So as you can see here, the voltage across T is smaller than voltage across R for the same current, right? For the same current of 0.4 ampere. This is the relationship between the voltage. Let's go back to the calculation here. So we know that whether R or T has the greater resistance. So we have resistance of T and we have resistance across R. R is these are the two components. So about the voltages, so when the current is the same for both of them, we have the two voltages, right? We have the voltage across R, we have the voltage across T, and then we just found out from the graph, a simple comparison, that the voltage across T is smaller than the voltage across R. And as we know, the resistance formula is voltage over current. So if this is the same, current is the same for both key components, the resistance is proportional to voltage. So smaller the voltage, smaller the resistance. So as a result, since T has a smaller voltage and the resistance is proportional to the voltage because the current is the same, the T will have smaller resistance as compared to R. So deduce without a numerical calculation whether R or T has a greater resistance. So R has a greater resistance than T because R has a higher voltage across it. So it needs more current, no, it needs more energy, more voltage for the same current to pass through. So R has a greater resistance. Yeah. So the resistance of R is bigger than resistance of T. Okay, next one, component R and T are placed in a circuit. Both meters are ideal. So ideal meter means if the ammeter is ideal, it means it has zero measurable resistance. And if the voltmeter is ideal, it means it has infinitely large resistance. Slider Z of the potentiometer is moved from Y to X. So this is a potentiometer. State what happens to the magnitude of the current in the ammeter. Okay. So this is a battery, so the negative terminal of the battery is always kept as 0 volt, and the positive terminal of the battery is kept at whatever the voltage of the battery is, V volt, called the EMF. Okay, so this entire line is at 0 volt because it is connected to the 0 terminal of the battery, and this entire line, all of this, because the ammeter acts like a 0 resistance wire, so it acts like a wire, so it will just, you can just pass through it. All of this is connected to V volt, so it will be V voltage. Okay, so V, and we have to decide what is here. So slider Z of the potentiometer is moved from Y to X. So when the slider Z is at Y here, you can see when it is at Y, we will receive 0 voltage here. So all of this will be 0, 0, 0. V minus 0 is V. So we receive the entire voltage. So when we are at Y, we receive a voltage of V across this voltmeter. As we move the pointer Z toward X, for example, when the pointer becomes here, then we will receive half the voltage. So it won't be 0 anymore, it will be V divided by 2 here. So for example, as we move closer to X, so for example, maybe here it might become even bigger. It might become like maybe 3/4 of V. And so it's increasing. So as the pointer Z moves from Y to X, the voltage at Z increases. As the voltage across Z is increasing, so this side of the voltage is increasing, the potential difference between the two terminals will decrease. It will decrease, decrease, decrease until the potentiometer reaches this point. So when the potentiometer reaches this point, this side has a voltage of V, this side also has a voltage of V, so V minus V is 0. Okay, so state what happens to the magnitude of the current in the ammeter. So initially the current will be maximum when the pointer is at Y, because you have maximum available voltage difference, and the current will be maximum. As the potentiometer is slided from Y to X, the potential difference across the terminal will decrease, it will drop, and as a result the current will also drop, because the current follows the voltage. They're directly proportional. So the current will decrease ultimately to 0 when the pointer reaches position X. Estimate with an explanation the voltmeter reading when the ammeter reads 0.2 ampere. So when the ammeter reads 0.2 ampere, okay. So let's just erase all of it, just make it more clear. Okay. Estimate with an explanation the voltmeter reading when the ammeter reads 0.2. So this ammeter is reading a current of 0.2 ampere. So this 0.2 ampere is passing through the voltmeter, and this 0.2 ampere, no current goes into the voltmeter, so this entire current just goes down, because the voltmeter has infinite resistance ideally, so there's no way current can go through the voltmeter, so the entire current just goes down here. And at the junction, current divides equally. Current divides into two parts, not equally. It will be equal if the two resistances are the same, but we don't know whether they're same or not. So people say there are two currents. So we call it I through R and I through T. These two currents. So we can also say that IR plus IT. So the current in the two branches must add up together to 0.2 ampere in order to make sure that charges are conserved. Right. So the current divides at the junction and follows to the same branch, and then it gets added up here again, giving us 0.2 ampere back here again. Okay. Now back to the question. Estimate the voltmeter reading where the ammeter reads 0.2 ampere. Okay. So if you go back to this graph, right? So we know the total current is 0.2, but we don't know how much is the individual current passing through T and R. But we definitely know that the sum of the two currents passing through T and R must add up to 0.2. That is one. Okay, so we have actually we have to take care of 2 points here. Let me draw a short circuit here a little bit. Okay? So we have one resistor here, and we have another resistor here. So this is T, this is R. Since both of them are in parallel circuit, they should share the same voltage. So the voltage is the same. So we have to look for what possible voltage can both of them take, and it must be the same because they are in parallel, such that the sum of the two current in the branches, so I of T and I of R, such that the sum of the two current in their branches can add up to 0.2. Right? For example, let's say, okay, maybe we think that the voltage across the terminal of the two resistors is maybe 5, because they're in parallel. Let's say that they have 5 voltage. Is it correct? Okay, let's see. It means that the current passing through the branches is 0.35. So 0.35 and 0.35 when the voltage across the two terminal is 5. 0.35, can you give us 0.2? No way. So this is wrong, right? So we have to kind of decrease. So decrease. Maybe what if at 2? So you have to do it like randomly, like hit and trial method. You have to like observe and see what same voltage can you choose for the two components because they're in parallel, so that the sum of the two current passing through their branches can be equal to 0.2. Let's check this 2 volt. So 2 volt. So the voltage across R is around 0.5, and the voltage across T is 0.15. Do they add up together? Add a 2 volt to give us 0.2, 0.5 plus 0.5. Yeah, so these two current add up together to give us 0.2. So let me explain what is happening here. If you make sure that the voltage across the parallel circuits of T and R component is 2 volt, then the current passing through each one of them will be, so the current passing through R, it will be 0.5, and the current passing through T will be 0.15, and they add up together to give us a current of 0.2 ampere, which is what is passing through the ammeter. So it has to be 2 volts. So 2 volts is your appropriate voltage to supply to this parallel circuit to make sure that the current passing through the branches is appropriate enough to add up together to give us 0.2 ampere. This is a little bit hard, but let's make sure that you follow it and understand it clearly. Yeah, so this is the explanation. Voltmeter reading. So the voltmeter will read 2 volt, and this 2 volt will be same across the two resistors because they're in parallel. In parallel circuits, the voltage stays the same. Only it is the current that divides at the branch. Okay. Question number 8. The following data are available for a natural gas power station that has a high efficiency. So the rate of consumption of natural gas is this much. Everything is given to us. Calculate with a suitable unit the electrical power output of the power station. Okay. So the rate of consumption of natural gas is like every second, this much kg of natural gas is consumed. Specific energy of natural gas is this much. Efficiency of the electrical power generation is this much. We have the efficiency. And mass of carbon dioxide generated per kg of natural gas is this much, and in 1 year we have, so 1 year has this much second. Okay, so imagine this is the generator, and this generator has some efficiency and it has some power output. So the power output is like energy output over time, and you have to give him some power input, which is equals to energy input over time. So let the time be 1 second. So just simplify things. So just replace this t by 1, so it just becomes equals to energy output. If you replace this time by 1, it becomes just energy input. Okay. So the formula is efficiency is output power over input power, and as you can see, when you replace time by 1 second, the output power becomes just output energy and the input power becomes just input energy. Okay, so electrical power output. So we need to find what is the output energy. So the output energy, if you make it subject, this epsilon, which is the efficiency, gets multiplied by input energy. So input energy times efficiency. Okay. Now, how do you find input energy supplied to the generator in 1 second? Well, it's very easy. So from here you can see in 1 second, so it's like you burn how much natural gas? 14.6 kg of natural gas is consumed every second. So we know we are giving 14.6 kg of natural gas, and if you burn 14.6 kg of natural gas, how much energy will be released? Well, if per kg of natural gas will release 55.5 megajoules of energy, then how much energy will be released by 14.6 kg? So simple multiplication. So just multiply specific energy by the amount of mass available. So this gives us this input energy. So this is the how much input energy is available in 1 second, and then multiply by efficiency, which is 0.15. Just make sure you convert the percentage into this fraction. So I repeat this thing. So 1 kg per kg, so 1 kg of natural gas when burned will release 55.5 megajoule of energy. Then how much energy will be released by 14.6 kg of natural gas? Simple multiplication. If you multiply these two, that will give you the total input energy. Just multiply all of this. This will give you the output energy. So the output energy, if you multiply them on the calculator, it will be 4.78 times 10 to the power of 8 joule. So 4.78 times 10 to the power of 8 joule. But as we already know that we take time as 1 second, so if you replace this t by 1, your output energy becomes equivalent to output power. So there we have it. This is just equivalent to output power also, because we take time as 1 second. So you can, for output power, we have calculate the mass of carbon dioxide generated in a year, assuming the power station operates continuously. Okay, so let's find out that in 1 year, how much natural gas do we burn? Because carbon dioxide is produced after burning natural gas, so we need to figure out how much natural gas do we burn in 1 year. So rate of consumption of natural gas is 40.6 kg burned every second. Then how much is burned in 1 year? Just multiply that. So 14.6 times the time, which is 1 year. So 1 year has this much second. So this gives us how much natural gas in kg to be burned in 1 year. And if you look at this thing, mass of carbon dioxide generated per kg of natural gas. So if 1 kg of natural gas when burned releases 2.75 kg of carbon dioxide, and this much mass will release how much carbon dioxide? Just multiply by the rate of carbon dioxide produced per kg of natural gas. So 2.75. Okay, so this gives us how much natural gas is available or burned in 1 year, multiplied by how much carbon dioxide is produced per kg of natural gas will give you the total carbon dioxide generated in 1 year. So this multiplied by this, multiplied by this, if you hit the calculator, the answer will be 1.27 times 10 to the power of 9 kg. 1.27 times 10 to the power of 9 kg of carbon dioxide is produced, yes. Unit is on kg. Explain using your answer to B why countries are being asked to decrease their dependence on fossil fuel. Because it's very clear from B that in 1 year period of time, the power station produces a lot of carbon dioxide. It's like around 1 ton of carbon dioxide, because it's like 10 to the power of 9 kg. And why carbon dioxide is not good for the climate is because carbon dioxide leads to global warming or greenhouse gas effect. So carbon dioxide is a gas that enhances the process of global warming by producing greenhouse gas effect. So they trap infrared radiations that is emitted from the ground, and then they radiate back to the earth and increasing the temperature of the overall atmosphere and causing the glacier to melt. So it's because the carbon dioxide leads to global warming, and global warming is caused by the greenhouse gas effect, so it causes climate change. So to avoid that, countries are being asked to reduce the dependency of fossil fuel, because when fossil fuels are burned, they release carbon dioxide. It causes greenhouse gas effect, causes global warming, and leads to climate change. Describe in terms of, we can also look at the mark scheme. What does it say? Climate change leading to enhanced global warming. So carbon dioxide is an enhanced gas that causes greenhouse effect and leads to global warming and climate change. Describe in terms of energy transfer how thermal energy of the burning gas becomes electrical energy. Okay, so let's look at the mark scheme. So when you burn a gas, right, the internal energy, the chemical and internal energy, so the internal energy in the form of chemical energy, the kinetic and potential energies of the particle. So the internal energy of the gas is given to the steam, right? So the steam contains kinetic energy because steam contains particles that are vibrating and moving at very high speed. So the steam has a lot of kinetic energy. So first of all, the chemical energy of the fuel is converted into internal energy of the steam. So the internal energy of the steam is mostly consists of kinetic energy because the steam moves at a very high pressure. And that high internal energy steam with high pressure causes the turbine to move. So when the turbine rotates, so the internal energy of the steam is converted into rotational kinetic energy of the turbines. And when the turbine moves, according to electromagnetic induction, the kinetic energy of the turbine is converted into electrical energy. So internal energy to kinetic energy, and then kinetic energy to electrical energy. Okay. All right. Thank you very much.